morning, everybody. So my name is Lukas Larsson. I work for Erlang Solutions, but I've been a consultant at Ericsson for at least more than a decade, working with the Erlang core team. So I'm developing the virtual machine, the compiler, the libraries, and so on around there. My experience with RabbitMQ is very limited, but I've been learning more recently. And this is a talk talking a bit about the history of Erlang and some of the unique characteristics of Erlang and what they bring to Rabbit. So I live in Stockholm, and this picture was taken about 1.5 kilometers from where I live about 1 century ago. So in the beginning of the 20th century, 1900s-ish. This is what a telephone tower looked like at that time. So this served roughly 4,000 abonnents of telephone in Stockholm, and all the lines you can see, you have frost running along them on an early winter morning. So you can see them very clearly, and it's quite a famous photo of Stockholm at that time. Stockholm was one of the earlier adopters of telephones in the world. We had a lot of telephones very early, and it created this thing. About in 1915, telephone companies started digging down the lines into the ground because they were quite vulnerable going in through the air. But this is what it looked like. This is around the place where NK is today, for those people that know Sweden or Stockholm there. And this was a huge mess. And it's this huge mess that Erlang eventually came into the world to solve. But first, there was a transition period. So we first tried to do something that was more mechanical and more things. So you had these things that were switchboard operators, where somebody would do a call, normally a lady, would answer saying, "Hi, who would you like to call?" Yes, I will connect you to the Svenssons on the other side of the street. And then they would connect you, and they would make sure that everything worked. This was a manual task for a very long time, going on all the way up to the invention of the computers in the 60s and 70s up there. And going along here, Ericsson, the company that invented Erlang, have always been working with trying to make telephoning more easy for everybody. So they founded a group somewhere in the 80s trying to make a new way of allowing people to communicate better through telephony. And they needed to have a solution where you wanted to have something that was highly parallel, because you have telephone lines going through and out. They are not interconnected. You're not talking to anybody else. They did not have group conversations at this time there. You want to have an emergency service that you can rely on, something that always gets you through, no matter what the snowstorm, no matter what happens. You want to be able to phone 911 or similar 112 to get through your emergency services. It cannot be offline, and you want something that, no matter how much that's going through the system, you want to be able to gracefully handle these kinds of things. And what they came up with, one of the solutions to this was Erlang the programming language. They tried various different things, and there was 3 engineers working at that time in the 1980s, 1990s, that decided that the way to go with this thing is that we should model our world in small, self-contained processes. And this is kind of the core concept of Erlang the language, which is not really the language, but it's so ingrained into the runtime and the language that everything is built around this concept, that you have small, isolated processes that run and do their thing and communicate with the world around them, very much like we are communicating in this room at the moment. We wanted to have, in this case, we want to have isolate these processes so that we can handle failures without a cascade failure happening. This was something that they took from the hardware switches and how they work, that you could have failures in the circuitry and it would just shut down that specific circuit and not infect the entire board. So if something broke, you would still operate the rest of the calls, because 112 calls and emergency calls are very important. You don't want the entire board to break just because you have a faulty circuit breaker somewhere, circuit in there somewhere. We want to have distributed computers because no matter how hard we try to make one thing work, it will fail eventually. The power will go out in that building. Something will happen. There will be a fire, something. So you want to have built-in distributed computing in this part because you need to have a backup if something goes terribly wrong. And you want to have what's called preemptive execution of these things so that nothing can get in the way of something that's more important than what's running at the moment, so that you can have things running, something running and then being paused and something more important coming in there. We're not really talking about something that's like hard real time in this regard, but something that gives some kind of fair execution to everything. If you want to have something that's hard real time, you need to be very, very careful with what you do, but there's a compromise to be made from something that's not real time at all and something that is hard real time. And these are the kind of the solutions that they were looking at and fixing. Wikipedia describes Erlang like this. So Erlang is a general purpose concurrent functional programming language with the garbage collected runtime system there. And the functional part has has grown out very obviously when you look at the set of specific limitations that they wanted to put on the systems. You couldn't make these kinds of systems with something that was at the time more procedural or destructive in its way. You wanted to isolate things so that you could isolate the failures in there. So I'm going to talk a bit about these processes that we are using in Erlang. So a process in Erlang is very, very similar to a process as it would run in Linux or on Windows. So it's a separate entity completely cut out from the rest of the system. If you want to communicate with somebody else, you need to interact with it somehow. There. You communicate between these processes by doing a message passing. So you send something, like sending something over a TCP channel or something like that. You send a message locally. There's no other way really to communicate with another process. This keeps them separate and isolated. The processes are preempted if they're not running too long. And one key thing in the fault handling in these things is that different processes can monitor the state of other processes so that you can see if this process, for some reason, a process died for some reason or crashed, it can do the appropriate action, restart it, or maybe just disconnect the current call or whatever it is that you're doing. There's two different primitives that we use here. It's either a link that ties two processes together, they cannot live without each other, or there's a monitor that says kind of that I want to know if this other process dies and then I will do something clever if that happens. I tend to view the Erlang virtual machine as a small cross-platform operating system running on top of your favorite operating system. So it's a small runtime with its own ideas, running on top of Linux, Windows, FreeBSD, whatever operating system you use in the end, and abstracting away on that. The distributing part, computing part, is that processes work the same way they do locally, they work distributed. So you use the same primitives to send messages, to monitor, and all of these things that you do on a local node, you also do in a distributed setting. And we have the code can be distributed to all of the different various nodes without having to recompile anything there. So it's very similar to the way that Java bytecode is compiled and distributed in that there. So some of the Erlang users of today, I thought I would introduce some of them to see if you recognize any of the names. So we have Ericsson is, well, the main user maybe. I don't know if it's the biggest one, but it's at least the one that invented the language, and they still use it to doing radio things. At one point in time, there was something like 60–70% of the mobiles, of all mobile internet data went through Erlang nodes. And that number fluctuates from decade to decade, but it's a lot. The whole world's 3G system, when 3G was a thing, almost all of it went through Erlang nodes at that point. And we have lots of different, Bosch uses it for various embedded systems. Cisco uses it for its configuration interface. So you have, anytime you buy a Cisco router, you have Erlang in that router. WhatsApp is one, don't have to say much about what they do. Cars.com do their web things in that. League of Legends do their chat in Erlang. Their Wargaming is a similar company, that World of Tanks and so on. They also do chatting. The NHS in England here uses Erlang, and also in the betting gambling industry, Bet365 uses Erlang for different parts. And the main event of this show, RabbitMQ, also is built on Erlang, which is the reason why I am here speaking there. So this is just a handful of the companies that use Erlang in some way. There are many more, but it's not a big language. It's a small niche language which has its advantages and its disadvantages. You get a small, tight-knit community where you can get to know the people that develop the language, and you get to know the people that use it in a small, tight-knit. But you don't have all of the libraries that would come to if you do something in the Java world or something in a bigger community. So it's a give and take. So now I'm going to talk a bit about Rabbit and the way that I understand Rabbit, which is probably not the way that Rabbit works there, but it's an approximation, something like that. So this is kind of the way. So we're talking about processes. So in RabbitMQ, when you do a connection, you spawn up a process. So when you have that connection into the cluster, you have one process handling in that connection. Then you can have multiple channels for each connection. So you can set up multiple channels that you talk in parallel. And that's one process per channel within that connection. And then you talk to some kind of queue. And each queue is also one process on the other side. So in a small RabbitMQ system, you have something like this on the screen running. So you have basically 3 processes running for each connection into the system. And then you have the central queue running there. And you talk in different ways in there. A single RabbitMQ node typically has something like 10,000 or 100,000 processes running in their system. There. So there's a lot of processes running at the same time, interacting in various ways and different things. And yeah, so let's see. So I'm going to talk about 4 of the properties of Erlang that I think shine through in the implementation of the RabbitMQ: fairness, isolation, parallelism, and the distributed computing parts. So let's start a bit with fairness. So every process has a small time slice to run, which is about 1 millisecond. So that's how long a process is allowed to run before it's scheduled out again. This means that long-running jobs that will do something compute heavy for a long time will only get half a millisecond, and then something else will be scheduled in, so that you will never have something that gets blocked for a long time because you fire off a report that needs to be generated, a big PDF of some sort that just keeps running and running and running and running. You will still accept new connections, handle the queues, and so on in your system. And even if you are totally overloaded in your system, you will still continue to make progress. The system will always try to make some sort of progress. And how do we measure these kinds of things? So if we run a RabbitMQ system, we have something where you have 2 queues that is fairly loaded. So I did some benchmarking, and on my in my benchmarks, I managed to get something. I got like 100K messages per second, and then I have a 99th percentile latency of about 1 millisecond on that. And then I have a second queue that is behaving quite normally, 2K messages per second, and it has a 0.6 millisecond latency. So it's serving things quite nicely. But then something happened. Somebody in the world releases a new gadget, and your system spikes. Something happens. And one of the 2 queues becomes very heavy loaded. So you have a system running at 100% CPU. You get something like 150,000 messages per second just pumping through the system. It's going on its knees trying to serve this. You get a latency of 50 milliseconds of all of these requests. It could spike higher. It could spike a lot higher depending on the system. But the key part here that what Erlang helps with is the second queue that is running, and it's not overloading the system. It's quite happy. and it's running along in the system, and it's increased its latency by 2 times. But it's still running, serving its customers as it should, while the one that's actually causing the load is the one that gets penalized in this situation. And I think that's the way you want to have it in a system. Isolation. So we want to keep things isolated so we can recover from failures and these things. So a failure or a crash of some sort only affects one single process. So these kinds of failures we're talking about is either something that is deliberate or something that is undeliberate. Because unfortunately, we as programmers make mistakes. Some assumption somewhere is incorrect. We did not anticipate that this thing could happen at the same time as this thing, or that when I did a database read, it returned an integer instead of a string for some reason because the DB admin had done something strange. Who knows what happens? So things happen in the real world, and we want to be able to isolate those failures so that we don't lose all of the data of the node at the same time. So we manage the errors at the process level to see that, okay, so it's this process that's there, and then we monitor it from the outside in order to see that, okay, so what should we do when this type of process fails? What should our actions be to do? Can we restart it? Can we reload the data from a database and restart the process? Or should we just disconnect the user and give them a 500 saying that, okay, the server crashed. We have a log somewhere saying more details about it, but you'll have to reconnect for the time being. Or what should we do? And depending on the error, different things will have to be done. And of course, you also need to do error handling at the local level so that you can actually give the user a good idea of what is happening. Is the database busy at the moment? Maybe you want to give some kind of better feedback than just a 500 to the user. So you need to have local error handling as well. But for the unforeseen, which will always happen because you can't foresee it, then you will be happy that it's only your small slice that gets affected there. So as an example, we've all been practicing self-isolation recently, so this should be second nature to us. If a queue, for instance, were to crash for some reason, it got a message it didn't expect, or it got some reason there, it will only affect its small part of the system, and depending on how the channels are set up and so on, it might cascade back to the user, or it will be stopped at the user, and then maybe the queue can be restarted. This is where my RabbitMQ knowledge reaches its limits, but something like that could happen. We also have the isolation on a per process level, which is useful. And in order to kind of communicate, I said we use message parsing in different ways. So any process needing to do communication, they send a message, a letter. And in Erlang, we have a single message queue going into a process. So you have one process and a single big message queue with all the messages going in. So you send it, you put it at the end of the list, keeping everything separated, because now, because we don't have any reference to the data on the original process, everything is copied, we can isolate that process and put it in one place there. And then the process in question will check its mailbox, look for the type of message it wants to handle at the moment. It looks through it, finds the message it was interested in, and then does some computation depending on that data. And that's kind of the gist of all of the communication methods within Erlang. It's simple, it's versatile, but it has its limits as well. But it's a good starting point, and it makes this that no data is shared also helps up when you try to do distributed computing on different nodes in there. We'll talk more about that later. We also have isolated garbage collection in Erlang. So every process is garbage collected individually, which means that we have a much smaller garbage collection problem than some of the other runtime systems, which means we can use a simpler garbage collector that is faster and easier to debug and easier to maintain and so on, because it's on a per process level instead of being larger in there. So just some basic garbage collection intro. What it does is that basically it copies all the data from the old instance to a new one, choop, choop, choop. And then in the new one, we have all of the data. So during this time, let's see, my slides are acting up a bit. During this time, as you can see, the memory consumption of a process doubles. So you can have points in the system where if you have a single process that has a huge amount of data, you can have points in your system where you're using double the amount of data temporarily in order to do a garbage collection. But in a normal running Erlang system, you should have really small processes so that this will not really show up in there. But let's see, I found this small tidbit in the RabbitMQ documentation saying that temporarily you can use about double the amount of memory that you use. And this is the reason why you do that, because garbage collection can, if you have a queue that is heavily loaded and use a lot of memory, it will spike that memory of that queue, and then it will try to do a garbage collection, and then it will double that memory, and possibly your Rabbit instance will fall over. Yeah, okay. See, it's Erlang running. They're self-correcting. There, so parallelism is one of the things that many associate with running Erlang. So when running an Erlang virtual machine, all of these small processes automatically get put out on all the different CPUs running on your system. So we have the different channels and queues. They are scheduled on the cores 1 and 2 over here. So no matter the size of your system that you're running on, Erlang will try to do the best and utilize the different cores that you have in your system. So if we have another message coming in from a AMQP client here, and then we see that, oh, now this core has a lot of things in its message queue that will be put out, rescheduled on a different core, and then migrated over there so that we try to use as much of the machine as possible, while also making it possible for the operating system to put cores to sleep to save energy when possible. So you're trying to make a best of both worlds, where we try to put as much load as we can on as few cores as we can, but as soon as they start to become overloaded, we migrate over and see that we try to use as much of the machine as possible. I know that there's been systems that have disconnected CPUs completely, so disable them in the operating system when they have low load, and then putting it up again when it's higher load in there, in order to save energy running there, or use that for something different in a cloud environment. Let's see. So the parallelism also ties in with fairness. Because in an overloaded system like this, the reason why we were able to have such a low latency on the queue that was running just a few thousand messages per second is because even if this seems like a perfectly utilized system, it's not fully balanced. So because we are running 4 processes on the 2 cores and then 3 processes on the other cores, and if these processes are running a lot of time, it will take a longer time for the processes on the cores 1 and 2 there to get their execution slice, because they have a longer time in the queue every time they get rescheduled. So for this system reason, we even out the load in the system when it's overloaded, so that you actually try to make sure that the queues on all of the different cores are the same, so that we make sure that the latency of all of the different processes is fairly managed between the different things running. There. And I did some benchmarking with this. So RabbitMQ does, or Erlang or RabbitMQ, I don't know what's the bottleneck at this, does not scale perfectly with the amount of cores, but it scales okay. So we start, when running 1 core and 1 queue, managed to get something like 40,000 messages per second running on 1 core. And then as we double in the beginning, it actually is kind of a linear progression of the amount of messages per second that the system can manage. But as you add more and more and more and more cores, you get a more gradual decline. And then at the end, at 40 cores, I maxed out at almost 1 million messages per second on that system, getting there. And there's a lot of reasons why you don't see a linear progression there, but normally there's something that is a sequential bottleneck in a system. There always tends to be there's a, I don't know if it's famous, but there's a person called Amdahl that describes something called the Amdahl's law that says that no matter how many parallel resources you have, if you have something that is sequential in nature in the middle, you cannot parallelize it, and your system will never be faster than that. And you always end up having something that is parallel. It could very well be that this is running on a Linux. It could be something in the TCP driver that needs to synchronize. That's the problem here. Or something in the, I don't know, the memory allocators in the operating system, or on the Erlang, or on RabbitMQ level. You don't know, and you have to look through the entire stack to see what happens. But I think it's quite impressive that it still continues to scale at 48 cores, and it would probably try to scale further. I tried running this on a machine that I have in our lab that's 224 cores, but that's kind of, it dipped after a while. It wasn't able to do there. It was too much overload. And the problem with these machines that have a lot, hundreds of cores, is that the individual CPUs are rather slow. So it's a give and take. Distributed computing. So the last part of this adventure. So anywhere in a system, you can start working out that, okay, so I'm starting small, I'm starting simple, I'm starting with one node, I'm trying to make this work. And then you realize kind of, okay, so I need to have 2 machines running this. And it's easier in Erlang than in other languages. It's not easy, but it's easier to just say that, okay, so I'm going to split this application in 2, put out 2 nodes, and then just use the same message passing going to and from there. You use the same primitives. Nothing changes in your applications, really. It allows the system to relatively easy scale horizontally as well as vertically there. So in there. I've seen systems with hundreds of nodes running there. I think somebody has gotten 1,000+ nodes running in a cluster, but it didn't do much more than just sit there and use all of the network. Distribution is not a silver bullet for networking. It has its limits. It's an easy use case to get started. It works in a small scale. When you get into big systems, complicated solutions, most people go away from using the distribution, but it works really well until a certain point, I would say. Originally, the design behind the distribution was in order to keep a small telephone blade running in a single rack at the same location, maybe having 2 or 4 nodes. And then it's been kind of growing and growing and growing in size as the whole cloud movement came along and tried to build bigger and bigger distributed systems. And it's tried to keep up. It's showing some of its flaws, but it's still working relatively well from the origins where it came. So what about Erlang the language? So I've talked a lot about the runtime system, because in my opinion, the runtime system is what's really unique and the competitive advantage around Erlang there. So Erlang the language is it's a strongly typed strong dynamic typing language, which means that it's kind of I don't know what it means. But that's what it says on Wikipedia that it is. Since I'm an Erlang person, I'm not a typing person, but somebody that knows types knows what that means. I should have looked that up, or remembered rather. The syntax draws heavily from Prolog. And Prolog is not the language that a lot of people get to know nowadays. So it's a bit foreign for a lot of people. It's very different. The language is built from the bottom up to complement the behaviors I've described in the virtual machine. So all of the different things that we're talking about, the distribution, the fairness, the isolation, and all of that, the language is built in order to emphasize those points in there. The language has remained roughly the same for, I would say, 20 years. There was a lot of changes happening in the 90s to various parts. But since the 90s and onwards, it's remained roughly the same. There's been some small tweaks here and there. Many other languages also target the Erlang virtual machine. It's kind of become a big revolution in languages, just as the JVM had a decade ago or two. So as the Erlang virtual machine, the biggest one at the moment, I think, is called Elixir, which is run by an amazing guy called Jose Vasilem there. But there's also Lisps running on Erlang. There's Haskell dialects handler running on Erlang. There's for every flavor of language that you would like, there is normally something running on the Erlang virtual machine as well. So you don't have to use the Prolog Erlang, or whatever you want to call it, the original Erlang, if you want to run on the virtual machine and get the properties I've talked about. The virtual machine has, in contrast to the language, received quite a lot of innovation. A lot of different things have happened in the virtual machines, in especially the last 20 years. 15, 17 years ago, the multi-processing support was added. So that's when we went from running on a single core to running on multiple cores. And that process has just continued and continued and continued. And it's one of the most exciting areas that we have in the virtual machine. Building things. Just very recently, we added a super scalable binary tree algorithm that you can use in your things to build trees of various sorts that works amazingly good on these 224 core machines that I mentioned. It scales to huge amounts of cores. And about 2 years ago, we got our first just-in-time compiler running inside of the Erlang virtual machine, which sped up a lot of programs, including RabbitMQ got about a 20% performance boost running there. It depends on what you do. Some programs get around a 50% performance boost, some programs get 0. So it depends on what your use case is in there. Yes. So there's a lot of things happening in the runtime system, and just this year we released support for the JIT with ARM as well. So now you can run it on x86 or ARM if you would like, which makes it really good to run it on these Apple laptops, really fast. That was all for me. A quick whirlwind tour about what Erlang is and what I think it brings to RabbitMQ as a product. I want to thank Gabor and Laos and the RabbitMQ team at Erlang Solutions for helping me to understand how to run the benchmarks of this product that you're all here and excited about. I've learned much more in the last month than I did before, which is good. So yeah, thank you.
So thank you very much, Lukas. This is really an opportunity for the audience, all those who are online, to ask Lukas some questions.
Yes, please.
So, okay.
Hey, Lukas, thank you. Really nice of you to speak about Erlang. I was an Erlang developer like till 2 years ago, and there's few things I saw different between Akka, actors, and Erlang processes. So there's a couple of questions, if that's fine. So this is not RabbitMQ, this is purely Erlang. Within Erlang, you've got mailboxes per process. Within Akka, I don't know what it's called, I don't remember, but something similar, right? One of the things we found is if we wanted to limit a particular task, let's say, account, right? I'm just giving you a use case, so account, and that account belongs to a central bank. And let's say the country has a king in that central bank, and you want that process to process the mailbox, to process all of the transactions, if you will, for that country, for that account, going through that mailbox, that one mailbox, yeah. What I found in Akka is, for example, you could have priorities set on the mailbox for a certain process, right? And maybe it's changed since 2 years, right? But on Erlang, we couldn't just say that certain messages have a higher priority, and which is maybe intentional in Erlang, but maybe that's moved on. But within the mailbox, there was no way to even look at the mailbox, for example, see how many messages you have when things are going slow, right? That's got lots of messages, right? So those are few things, right? Inspecting the mailbox, setting priorities within the mailbox, having different strategies for the mailbox messages to be processed by the same Erlang process, right? So I have another question, but that was...
Okay, so yes, this is one of the things that gets brought up a lot. It has not changed in the last 2 years there, and I don't think it will change because it's one of the things that would ruin the scalability of what we're trying to do with the mailboxes and so on. Putting guarantees and putting that kinds of features inside of the recipient limits the way that we can make optimizations and scalability improvements. Because every time you introduce some kind of inspection or some kind of way to monitor different things, you normally put in some kind of scalability bottleneck in these parts. So you have to think very, very carefully about what things you put in there. And Akka has done different trade-offs than we have done so far there. But it's a discussion that keeps coming up all the time, and eventually maybe we will have something like that. But at the moment, there's no real plans to do anything like that. And the priority message things is kind of, you need to do what's called a selective receive. So you kind of scan the mailbox looking for the thing, as I showed in the slides there. So you're looking for, you tag something saying this is a high priority, and then you look through your entire pile of messages that came to your door saying, okay, which ones are flagged high priority? There's no way to just have a separate pile of messages that are high priority. So yeah.
Yeah, I mean, there are ways around it. I mean, in Nisia, what you could do is you could just read from Nisia instead of a mailbox, and then in Nisia you can have various tables, some high priority, and keep checking. So there are ways around it.
Yeah.
But the other question I had is, one of the banes, we deploy payment systems to various countries. Every country has a preference, or a vendor. They might go IBM, AIX, for example, or Solaris. And many times the Erlang compiled, or of course we can compile for an environment, but then you need to get into what for example ncurses needs to be deployed at this version for this version of Erlang and things like that, right? So and it seems to be a bit random, that or maybe it is not. Let us know. Is that it works on certain machines, but will not be pre-compiled for certain machines, and then you got to go from ground up to compile it in those environments. So
we at Ericsson are not really in the business of providing pre-compiled binaries doing that. That's a community effort for different environments, and I guess that's driven by popularity. What environments are pre-compiled. I know that the RabbitMQ team at VMware provides a lot of different images to run RabbitMQ in different parts where they've done a great effort, I would say, to get that working. But we are not really, at the Ericsson part, are not interested in doing that. And the community, I think, has pulled up the slack relatively well, but not in all the places you would wish.
Thank you very much for that question. We have an online question from Stefano. So, Stefano, can you ask your question? If you can switch your camera on and come online. Unmute yourself.
Yes, can you hear me?
Yes, we can hear you just about.
Okay. Yeah, I asked if it is possible to identify the CPU usage of a single queue.
That's really a RabbitMQ question, but I would say that's a hard parallel to make to measure to see how much a single queue makes, because inside of the Erlang runtime system, we count something called a reduction, which is basically how many function calls a single process has done. And that does not really translate over to something that you would be more familiar with. But you can compare then a single queue to all the other queues and get a relative scale to see, okay, this queue is using 25% of the queue execution resources while running on the other parts.
There's a Rabbit performance session in the afternoon. I'm not saying we will answer this specific question, but we'll have a RabbitMQ performance session in the afternoon, and yeah, we will not necessarily answer this very question because there is no easy answer, I guess. But we will show you some tools that we use to improve Rabbit performance.
Perfect. Go to that session.
Thank you very much for that question. Okay, we have another question.
Hello. So you mentioned the Erlang the Language didn't change much, yet recently you just introduced a maybe proposal. Are there any new exciting things you know that will be added to the language? There's
things we are looking at, but there's no things that are decided as yet. This is going to have to be on the top of what I recall, but from what I recall, the discussions that we're talking about at the moment is adding map comprehensions to the language. We are talking about possibly adding some kind of namespacing in there, and I don't, maybe, this is going to be iffy, but maybe something with the string syntax. I'm not part really of that group that looks at these things, but it's you hear rumors in the coffee table. So that's the things that we are kind of looking at the moment, I believe.
Thank you for that question. Dart across here.
Hi, Lukas.
Hi.
Thanks a lot for a good presentation on Erlang. I don't know Erlang, and it was very good for me to learn all this stuff. So you mentioned that fairness is achieved by scheduling every process for 1 millisecond. So how CPU affinity issue affects that fairness? Because if you have more CPUs, your process can be rescheduled on another CPU, so you need to copy some stuff from memory into CPU. So how you solve that problem?
I mean, the operating system does the copying for us, kind of, but you get issues with different CPUs getting different parts. And the Erlang processes don't migrate across the distribution boundary. So that's kind of, if that was a misunderstanding. So just to be clear, Erlang processes, they are rescheduled and managed on a single machine, single node. And then with the CPU locality running in there, so we try to make sure that all of the different threads that run a single thing are spread out on the different cores, so they are locked in place. And we try to, the compaction things that I was talking about, make sure that we try to stay on the same CPU as much as possible.
All right.
But you are correct in saying that since we rescheduled so often, we will need to fetch data from another process that does a different thing all the time. So all the caches will be flushed at that point. Yes, that's a trade-off you kind of have to make when you make more soft real-time systems, that you are rescheduling a lot.
All right, thank you.
Oh, no problem.
So much. Do you have any other questions? Okay, please give a round of applause for Lukas.
Thank you.
Yeah.